So 6.5 is about a specific type of differential equation, and it's a differential equation that uses proportionality. We're familiar with direct variation. We're going to use a direct variation equation and then solve the differential equation, and we're going to develop a formula that we're probably familiar with from Algebra 2. That's the law of growth and decay. All right, so just as a reminder, if something says that y is proportional to x or y varies directly as x, that means that we have a relationship y equals kx, okay, where y and x are varying directly, and this is your variation constant. Okay, the law of growth or decay says that the rate of change of a population is proportional to the current population. Now, not all populations follow the law of growth, but if the law of growth models a particular population, then what we can have is a relationship where we have a differential equation where rate of change is one of our variables and current population is the other variable. So if I use P for population, then I can write an equation that rate of change of population with respect to time, so dP over dt, is equal to a variation constant times population. So this is a direct variation relationship where my variables are rate of change of population and current population, okay? And again, K is a constant. So now that we have a differential equation, we know how to solve this, all right? So we're going to multiply both sides by the dt, divide by the p, and we have 1 over p dp is equal to K times dt, and then we integrate both sides. The antiderivative of 1 over p, like we saw with the slope fields, is the natural log of the absolute value of p, okay? And then the antiderivative of k dt. Now, pay close attention here. K is a constant, but even if it was a variable, this is an integral with respect to t, as in t is the variable in this expression. So kx is a constant, even if it was a variable, here it would be a constant. So the antiderivative of essentially k times 1 with respect to t would be 1t with a coefficient of k. So that's kt, and then remember we need a plus c. Okay, and now we're going to solve for p. So we start by taking the exponential of both sides, and then e to the natural log of absolute value of p. The e and the natural log cancel out, so we have absolute value of p equals e to the kt plus c. And then here, I want to do something algebraically. Remember, we have rules of exponents that say if we are adding in the exponent, that's the same as multiplying the two bases. So what I mean by that is if we have like a to the m times a to the n, that's a to the m plus n. Well, I'm going to go backwards this time. Instead of having a sum in my exponent, I'm going to write it as the product of two terms with a base of e. So that's e to the kt times e to the c. And remember, c represents any constant. At this point, because I haven't plugged in an initial condition, okay, I can do things to the constant c and just keep it as c. So in other words, e to the c is still just a constant, so I could also write that as c, I'm moving it to the front, times e to the kt. All right, so e to the c, still a constant, c, still a constant, and it's still any constant, so it is okay to make that switch. And again, I just move that to the front so that it is in order, okay? Now, when we are talking about population, we can't have a negative population, okay? Normally, if we're solving a differential equation and we have absolute value bars around this, we have to have a plus or minus to take care of the possibility of a positive or negative for whatever is inside here, okay? We saw that with the slope field notes. But here, it is okay to just say P equals, and we don't need a plus or minus because, there's no negative population, unless there were zombies. Maybe if there were zombies, then those would count as negative. I don't really know, but no zombies, so no plus or minus necessary, okay? Zombies would complicate the calculus. So we have some constant times e to the kt. This may be starting to look familiar, okay? This is actually a formula that we are familiar with, but it's not quite using the same variables that we do or that we're familiar with just yet. Let's talk about this constant, okay? Remember, the C can be anything, but it is something specific here, okay? If I were to plug 0 in for t, so I'm going to actually write this, when t equals 0, in other words, the initial time, then this would be equal to c times e to the 0, which is just c times 1. So c, okay? In other words, when time is equal to 0, the population is equal to c. That means that c is the initial population. Okay, so we can write that population is equal to the initial population. I'm going to write that as P sub 0 times e to the kt. This is our law of growth formula. Okay, now you might be more familiar with it like this. Y equals P times e to the RT. Okay, if you remember the formula PERT for law of growth. All right, it's the same thing. We're using K as our variation constant instead of R, and then P sub 0 is P. And I ran out of time because class is about to start, so I will finish this video in another video, or finish these notes in another video.